properties of Laplace transform. See, up to now I have explained the basic signals Laplace transform, and now we have to discuss properties, because properties are used to simplify the equations easily, right? So for easy simplification purpose, properties are used, and in that one standard property is linearity property. Linearity property. See, linearity property, that name explains the total response is sum of individual response, or we can write one standard statement like this: if the system or if the signal satisfies the superposition theorem and homogeneity theorem, then it is a linear system. So that from the superposition theorem we can write total response is equal to sum of individual response. Now we have to write that linearity property in Laplace transform. For that purpose, first of all I am taking here individual response, like Laplace transform of x1 of t. x1 of t is one function, right? One different signal. Laplace transform of x1 of t becomes here x1 of s. Because Laplace transform is used to convert time domain to frequency domain. Time domain function is x1 of t, that's why the frequency domain representation is x1 of s. And similarly, now I am taking some other function here, another signal. Laplace transform of x2 of t is x2 of s. So time domain is converted into frequency domain. This signal is other signal, and this is some other signal. x1 of t and x2 of t, two different signals I am taking. Now I want to find the Laplace transform of summation of these two functions, like, so Laplace transform of x1 of t plus x2 of t. And again these two functions are multiplied with some constant here, a, and here b is there, right? So this is called total response. So now we want total response. Linearity property, the name explains the total response is equal to sum of individual responses. So already we have discussed Laplace transform of x1 of t is x1 of s. This is one individual response, plus Laplace transform of x2 of t is x2 of s. This is another individual response. So total response is equal to sum of individual responses, and constant multiplies as it is. So here a constant multiplies, then write here a, and here b is multiplies. This is b. This is the statement of linearity property of Laplace transform from the Laplace transform. Linearity property from the Laplace transform. So Laplace transform of a into x1 of t plus b into x2 of t is Laplace transform a into Laplace transform of x1 of t plus b into Laplace transform of x2 of t. So to find the total Laplace transform, we can apply individually also. From this, for easy understanding purpose, now I am taking one simple example here. One simple problem is given like this: x of t is e to the power of minus 2t into u of t plus e to the power of minus 4t into u of t. See, now one signal is defined like this: summation of two individual signals. One signal is e to the power of minus 2t and another signal is e to the power of minus 4t, and both the functions are multiplied with u of t, unit step function. That means the time limits are from 0 to infinity only. Now I want to find out Laplace transform of this. So Laplace transform of x of t is x of s. Laplace transform of x of t is x of s. Then we have to write like this: Laplace transform of e to the power of minus 2t into u of t plus e to the power of minus 4t into u of t. Now I want to apply linearity property here. So linearity property explains total response is equal to sum of individual responses. So we can apply Laplace transform individually also. So for that purpose, here directly I am applying here Laplace transform of e to the power of minus 2t into u of t plus Laplace transform of e to the power of minus 4t into u of t. So individually I have applied, right? Just now we have discussed the basic equation, standard equation, that is like this: Laplace transform of e to the power of minus 8 into u of t is Laplace transform of e to the power of minus 8 into u of t is 1 by s plus a, with ROC is greater than the minus a. So this is one standard formula here from the Laplace transform. Laplace transform of e to the power of minus at into u of t is 1 by s plus a, and ROC is defined like this: s is greater than the minus a. Now these two functions are similar to this formula, and here a value is 2 and here a value is 4. Then directly I am writing now this x of s is Laplace transform of e to the power of minus 2t into u of t. From this, here a value is 2, then directly which gives the 1 by s plus 2 with ROC is greater than the minus 2 plus and Laplace transform of e to the power of minus 4t becomes 1 by s plus 4 with ROC is greater than the minus 4. So finally, time domain function is converted into frequency domain. So time domain signal is the signal, and frequency domain function is 1 by s plus 2 plus 1 by s plus 4. And individual ROCs are there. One signal ROC is greater than the minus 2 and other signal ROC is greater than the minus 4. Now we have to write complete signal, the complete signal ROC. So the total signal ROC. To write that purpose, always we have to take the common ROC from these two. Common ROC. This is defined from minus 2 onwards, and this is defined from minus 4 onwards, and the two ROCs are defined from minus 2 onwards. That should be like this. So individual I am taking now. So imaginary axis, this is real axis, negative real axis, right? So individually I am drawing now one ROC, one signal ROC is defined from minus 2 onwards. Just indicate like this, greater than the minus 2. This explains the one signal ROC, right? And another signal, one more signal is there that is defined from minus 4 onwards. So one more signal ROC is defined from minus 4. So minus 4 is located here. Then we have to draw another signal ROC is like this here. For easy understanding purpose, I am writing in different direction. So I am drawing like this, inclined line. Then both the ROCs are defined from which position? So you just compare this one. This is only one function is defined. From here onwards, both are defined. That's why your overall ROC is defined from greater than the minus 2. Right? So immediately we have to write that one now. X of s is, take LCM here, write s plus 4 this side and s plus 2 this side, then which becomes 2s plus 6 by s plus 2 into s plus 4, the complete simplified expression, and later this signal ROC is defined from minus 2 onwards, so greater than the minus 2. Then draw the ROC is from minus 2 onwards. It should be like this. This is the ROC of the complete signal or given signal. See, whenever the signal consists of summation of more than the one function, algebraic summation of more than the one function, then immediately we have to take the ROC is common ROC from the individual signals. Common ROC from the individual signals. Then the overall ROC of the given signal is greater than the minus 2. And the complete function is like this. Right? So this is another one example I have explained from the linearity property. And one more function I am taking now. This is another problem. X of t is e to the power of minus t into u of t plus e to the power of 2t into u of t. So now again the signal is summation of two functions. Then directly I am writing now. Laplace transform of x of t is x of s. E to the power of minus t into u of t. This is looks like this one, right? So then directly I am writing now answer is 1 by s plus 1. ROC is greater than the minus 1. Plus e to the power of 2t, 1 by s minus 2. ROC is greater than the 2. So one signal ROC is defined from minus 1 onwards, another signal ROC is defined from 2 onwards. Then the total signal ROC is defined from 2 onwards. Common area we have to take. So finally the x of s is 1 by s plus 1 plus 1 by s minus 2, and ROC is greater than the 2. So this is the answer, exact answer of the given problem. And if you want to simplify here, simplify this, take LCM, write s minus 2 here and s plus 1 here, then simplify that expression, write the answer, and ROC is always explains greater than the 2. So these are basic examples, simple examples from the linearity property, right? So please take this now.